Hello everyone, thank you for watching our video. My name is Min-Jung Kim. This work is done in collaboration with Gyojung and Jaegul Choo. I'm going to be talking about our work LensNeRF, rethinking volume rendering based on thin-lens camera model. Recent advances in NeRF show promising results in novel view synthesis tasks. However, NeRF-based methods generally assume that images are captured using a pinhole camera, and subjects and images are all in focus by tacit agreement. Such an assumption hinders NeRF-based methods from using images with defocus blur. So, we propose aperture-aware NeRF, which is called LensNeRF. Using a thin-lens camera model, LensNeRF allows defocus images of any aperture size as input and output. This figure shows the overview of our LensNeRF model. To generalize a pinhole camera model to a thin-lens camera model, we define multiple rays originating from the aperture area. The color of a pixel is considered as the integration of rays. Estimated pixel color is used for photometric loss computation, updating LensNeRF parameters. For the purpose of acquiring ray origins, regular grid sampling is executed within the aperture area. Please note that the ray origins are expressed with respect to the aperture radius AR, which has pixel unit. However, to sample points along the ray in 3D space for volume rendering, ray origins should be expressed in 3D space coordinates. To obtain scale that converts the 3D space unit to the pixel unit, we optimize scale explicitly. To make gradients flow towards the scale, the sample position is concatenated with MLP inputs. Orange arrows in the figure represent the path where gradients flow during optimization. As mentioned in the previous slide, LensNeRF tries to minimize the photometric loss during training. For additional ambiguity relaxation for deblurring task, we present the in-focus loss. This loss forces the color of the sampled 3D points to have the color of the pixel. If the 3D points are close to the focus plane. For instance, from the figure, assigning the green color of PI prime to the focus plane of camera 2 not only helps to determine the true color of a given 3D point, but also helps to narrow down the possible color compositions for gray pixel PI, removing trivial solution like assigning gray pick color to all 3D points. Through the experiments, we discovered that jointly optimizing scale and NeRF parameters from scratch generally leads to failure in convergence. Therefore, we periodically reinitialized NeRF parameters during training. We set the weights of the MLP layer, which are multiplied with the viewing direction, to 0 and freeze them in the initial inner loop. This process helps the NeRF network first learn view-independent colors. In the following inner loop, it develops view-dependent colors from the initially learned view-independent ones. To rigorously evaluate our proposed method, we construct a dataset of 9 scenes with varying aperture sizes. Each scene consists of images taken from different viewpoints. For each viewpoint, we collect 4 images with different f numbers. Check the sample images of the given f number in the figure. We conducted an ablation study to show the effectiveness of each proposed component. From this, we can verify that using in-focus loss is advantageous for the deblurring task. Scale optimization also contributes to the impressive performance enhancement. The figure illustrates the qualitative results of deblur task. Based on the outcomes, we confirm that the proposed method can synthesize crispy novel view images solely from defocused training images. The first raw displays the sampled training images. Notice the difference between the image domain of the training set and that of the test set. Despite the dissimilarity, our LensNeRF successfully generates novel view images that closely resemble the ground truth. Here, qualitative results on the defocus task are shown in the figure. As we can see, the proposed LensNeRF successfully modeled the defocus blur that reflects the depth variation. The video shows the defocus task results. Here, using the network trained on sharp images, novel view images with varying aperture sizes are generated. Results of our LensNeRF are compared with those of NeRFocus and DOF-NeRF. The video shows the D-blur task results. Here, using the networks trained on defocus images, sharp novel view images with varying camera poses are generated. The sharper the results are, the better the model is. We compare our LensNeRF with KPAC plus DVGO, D-blur NeRF, and DOF-NeRF in the video. This video shows the novel view images rendered using LensNeRF. Given the sharp images, our LensNeRF can synthesize novel views with varying aperture sizes, focal lengths, and camera poses. For more details, please check our paper. Thanks for watching.